What we're going to talk about in this section is the actual asphalt material itself. Again, it can be called asphalt cement, asphalt binder. A lot of different terms for it. Depending on the state and the specification, but essentially what we're referring to is the liquid asphalt itself. We'll talk about historic paving grade asphalts. We're going to talk about other delivery systems for asphalt, including cutbacks and emulsions. And then we'll close with the PG binder grades and go through that a little bit. Basically, asphalt, it is a naturally occurring product. If you've been to the La Brea tar pits in California, for example, that's an example of a natural asphalt deposit. They're actually, and it impacts our market in the United States. There are natural asphalt deposits in Trinidad and down in Venezuela. And historically, particularly early in the process, that was the asphalt that was used for a lot of the roads that were built in the 1920s and 30s. And when you get to the East Coast and the Southeast, it's relatively easy to barge that natural asphalt up across the Gulf to the Intercoastal Canal and wind your way up the Intercoastal Canal all the way from the refineries on the Texas coast up to New England. And it sounds like that shouldn't impact us. And in general, in our part of the world, upper Great Plains, upper Rocky Mountains, northern Rocky Mountains, yeah, we don't use natural asphalt deposits, so to speak. And but we get impacted by it because when the ripples hit, like when Venezuela closed down kind of all exports a number of years ago, that started shutting down asphalt terminals on the East Coast and in Texas. And when that happened, guess what? They had to start grabbing supply further and further back into the Midwest and mid-central United States. And all of a sudden, you saw prices rising for asphalt in Sioux City, Iowa. And you're going, well, how can that happen from a market impact in Venezuela? Well, because those natural asphalts that were coming up by barge through the Intercoastal Canal weren't available anymore. And as a matter of fact, they're very high quality asphalts too, believe it or not, those natural asphalt deposits. But in general, in our part of the world, when we talk about asphalt or asphalt binder, we're talking about petroleum asphalts. They're a product of the refining process of crude oil. As I mentioned, the first top mix asphalts were constructed in the 1870s. Actually, Pennsylvania Avenue between the Capitol Building and the White House was one of the first paved roads, and they used these natural asphalts. This is in Trinidad. This is a lake of asphalt, basically. I don't think you want to go walleye fishing there, but this is very high quality asphalt, obviously, for pretty low viscosity, low resistance, so easy to pump, and very accessible. Obviously, as the demand for roads increased, particularly through the late 1800s and the development of the automobile, primarily, the need for additional asphalt to build new roads increased dramatically. So we get into petroleum asphalts, and again, we're talking about refined crude oil, asphalt coming from the refined crude oil process. And if you look in front of you now, you should kind of have a basic schematic of a refinery operation. When I first got out of school, went to work for Texaco in the engineering department in Houston. Almost immediately, because of a strike, I ended up out at the refinery in Port Arthur, Texas, which is right on the border with Louisiana on the Sabine River, Sabine Lake, and the Gulf Coast. And it's a lot more complicated than this, but this is the basic schematic. Is with field crude oil, it's brought in, it's pumped in, it's tanked, field stored, and then it goes into the refining units, and plural is typical. And one of these units, and I just wanted to bring it up, is this distillation unit. And distillation applies high temperatures and pressure to that crude oil. And as it does so, it breaks the components of that crude oil down. And in general, the gases that come off the top, which would be pentane, heptane, propane, those are easily collected. Doesn't take any temperature really to do that. and they're collected and cleaned and stored and pumped out. And then next lower on the tower is the light distillates. And the light distillates, again, they're typically like your gasolines, kerosenes, diesel fuels, and then as you keep putting more heat and more pressure to that crude oil, the components break off. You end up with the light distillates, and then the medium distillates are like your fuel oils. We'll get around to that. But on the asphalt side, it's that bottom. They call it bottoms in the refining industry because that's what's left after you break the crude oil down. What's left at the bottom of the tower, the real heavy distillates, are your asphalt. And this schematic calls it residuum. It's the residual of the refining or cracking. I worked on a cat cracking, fluid catalytic cracking unit in Port Arthur, ran 60,000 barrels a day. A much more efficient method of breaking the crude oil down. So it's this residual off the bottom of the tower that generates the asphalt that we use in our industry. And then it can be processed and reprocessed, and you kind of see that in the lower right-hand corner of the schematic. The thing I want to bring up is what comes out on the bottom right-hand side depends on what goes in at the upper left-hand side. So for those of you from North Dakota, for example, or even western South Dakota, is Williston, Bakken formation crude. It has literally no asphalt in it. There's no heavy portion of it. In fact, I've heard and taught classes and talked to enough people through my travels across North Dakota. I've heard like the hot oil pumpers, if they start running out of diesel fuel and they're out in the middle of nowhere, they'll load the tank right in. I imagine it can't be good on the filters and the condensation process in their fuel tank, but they'll use it for fuel, essentially straight off the pump. And so it's very light. If you've ever seen a sample of Bakken crude and put it in a beaker at room temperature, it's relatively low viscosity, and it almost looks like the color of a really diluted Diet Coke. And but you have other oils, crude oils. A lot of the Wyoming ones I was used to, in Casper and Midwest, Edgerton area, are heavy crudes, and so they get a lot of the bottoms processed. They're a lot harder to crack, a lot more expensive to crack, and get the light distillate out. But the other takeaway from this is no refineries in business to produce residual. They want to produce gasoline because that's the highest margin, and more diesel and gasoline are kind of controlling the process, both from what goes into the refinery and what comes out. So this is just the classic breakdown. This is actually in that black book I mentioned, the Hot Mix Asphalt Paving Handbook. It's also in MS-22, which is the Asphalt Institute reference material. It's just the distillation chart. As you keep adding temperature and to the crude oil, the first thing right off the bat are the gases, meaning the pentane, heptane, propane, so forth. Then the next thing as you're breaking it off, the light end product is at lower temperatures, as far as breaking temperatures, are the gasolines, the naphthas is what it's called in the refining industry, because you refine the naphtha into gasoline, cleaning it up and adding, putting additives in to increase the octane. And then the next thing off is kerosene or jet fuel and diesel. And then gas oils or the fuel oils. And then the last thing left in the bottom of the drum is the asphalt residual or the asphalt. Couple things to remember is asphalt's got some really unique properties. It's kind of interesting that kind of the two products that are seen the most basic probably are the most complicated. And one of those is water. Water is one of the few products that expands when it freezes. Asphalt's really interesting too because it's actually a thermoplastic viscous material. In other words, in clean terms, is at higher temperatures, 70 degrees Fahrenheit going up to 200 degrees centigrade, it becomes a liquid. But as it cools off, it's a solid. And so we call it a thermoplastic material because as it is heated, it becomes less viscous. In other words, flows a lot more easily, flows more like water. And as it cools off, it becomes a solid, semi-solid. So it's an important thing to remember, both from the standpoint of obviously processing and mixing, but when even compacting asphalt pavements, that property comes into play. The three basic delivery methods for the asphalt itself are sometimes called neat asphalt, which is unmodified asphalt. In other words, straight from the refinery. It might be blended, but there's no other modifier put in. Or modified asphalt, where you put some type of modifier, whether it's SBR, SBS, styrene butadiene type products, polymer type products, latex type products, are blended in with the asphalt. But those are basically the paving grade. But the other two methods of delivering asphalt in construction are cutback asphalts and emulsified asphalts, and we'll talk about that. And the basic change here is going back to that thermoplastic property is back in the 1920s, there weren't exactly hot plants behind every tree, right, across the Dakotas. So how did you pave a road? You had no way to heat up a paving grade asphalt. There's no still, no way to heat it up to get the viscosity down so you could mix it with aggregate and get it hauled and placed. And so you had to use another method to reduce that viscosity, and that's essentially what generated number 2 and number 3 here that we're going to talk about. Before we get into a lot of detail on that, I wanted to talk about the specifications. From the late 1800s on, basically you specified asphalt. You need some type of specification, right? Get what you ask for, get what you measure. It was called penetration grading, sometimes shortened to called pen graded. And it was a simple test. You essentially had this tin of asphalt at room temperature in that cup, and you put a weighted needle on it, and in 5 seconds determined how far that needle penetrated into the asphalt sample. So the number you get in a penetration graded actually is a distance. And what's kind of interesting about this is that because this is one of the older tests in AASHTO and ASTM, is penetration grading of asphalt, was why room temperature? Well, you could test it any place across the United States. If you were in the middle of the Dakotas or middle of Wyoming, and you didn't have an oven to heat it up to a certain specified temperature, and even if you did, you didn't have a way of measuring that temperature. So it's kind of a room temperature test. 100 grams, I mean, that's fairly simple to weigh out. Probably a postal scale will do that. And then the needle itself is a Sears sewing machine number 10 needle. You might ask, well, why that? Well, you could order it any place in the United States. If you had a catalog, you could order number 10 Sears sewing machine needles, and that was the basic conception of the penetration test. And now, of course, AASHTO took over, and if you try and buy one of these needles to run a pen test, it's going to cost you hundreds of bucks ordering it from a lab supply house. But basically, that's the very simple beginnings and at room temperature. So if we look at this is the actual AASHTO specification, penetration graded asphalt specification for asphalt cement. There are two things, and hopefully everybody can see these okay. I put a box around primarily two things. One is the penetration, and you can see that's the upper line there. Penetration at 77 degrees Fahrenheit, 100 grams, 5 seconds. So just like we looked at in the previous schematic. The test method itself is AASHTO T49, and then there's the comparable ASTM test method. But it separated it then into 5 grades of paving grade asphalt. 40 to 50, 60 to 70, 85 to 100, 120 to 150, and 200 to 300. That's a distance that needle penetrated or penetrates into the asphalt. So when you look at that on the far left side, the 40-50, that's a very stiff asphalt, isn't it? It barely penetrated into the top of that little tin of asphalt. You get over to the 200 and 300, guess what? High pen number means very soft asphalt. That needle was dropping down to the bottom of the can, so to speak. So just a thing to remember, and we'll get at the reason for kind of still retaining this pen graded idea is, number one, a lot of our older pavements, when we look at them for wrap, were built with an asphalt specification that was pen graded. penetration graded. 85 to 100 was kind of a standard pen graded asphalt cement that was used long before PG binder specification. The next thing I wanted to point out was, and it's boxed in there, is flash point. Flash point is the temperature at what any product, given its volatility and ignition source, will essentially go to flame, combust. And so you can see asphalt, obviously when it's really stiff, it's 450 degrees Fahrenheit plus. So, not very many places in nature you're going to get to 450 degrees plus. You don't have to worry about a flash or a fire. Softer the grade, the more lighter ends that are probably in that asphalt. So the 200, 300 is about 100 degrees lower. And after that, there was a thin film oven test and then a ductility test on that residual. And then when you're looking at purity, the bottom line there was solubility, and trichloroethylene is just a quality test, the test for contaminants. You can see that. So basic takeaway here is really penetration graded. The higher, there were the 5 grades basically of paving grade asphalt under the pen grade system, from left to right, low to high, stiffer to softer asphalt. So if you were doing a high traffic volume road with real concentrated loads, you didn't want to put a 120, 150 pen grade in it. You wanted to use a stiffer asphalt or it was going to rot or move on. The problem, of course, one of the problems with penetration graded is, how often are we at 77 degrees exactly in the Dakotas when we're constructing or mixing asphalt? Not very often, so they went to a viscosity graded system, and this was in the 1950s. Viscosity is the resistance of a material or a liquid to flow. So essentially it's a tube. In the case of straight viscosity versus under some type of vacuum, is you put an amount of asphalt into the tube and measure its flow from the marks there on the pitot tube on the left side and see how far it flows in a certain amount of time. So the next kind of standard specification that's out there, particularly if you're looking at RAP and original pavements, was AASHTO M226, which was the viscosity graded asphalt cement specification. And I lined out that first line. First thing to note is that first line in the spec is the test is done at 140 degrees Fahrenheit. So now at least we can kind of make an analysis that, how often do we get to 140? Well, probably the middle of the summer, right? You get 5, 6, 7 days, real hot days in a row, or it doesn't cool off at night. You can get pavement temperatures up to 130, 140 degrees, right? The middle of the 5th day or 6th day. And asphalt, again, what we're dealing with essentially on one side is we don't want it to rut, we want it to be durable. Well, if it's going to rut, typically it's going to rut because the asphalt's soft. So we're kind of getting a test that we can use, a specification that we can use to control a little bit of the stability side of the asphalt A in the 3 A's of our asphalt mix. So as we look across, you can see there were 6 grades in the viscosity graded AC, from AC 2.5 up to AC 40. As you go up the line, essentially that's a set point with a tolerance on viscosity measured in Poises. And so as we're going left to right now on the viscosity chart, the material's getting stiffer, right? Higher viscosity number, stiffer material. So for example, when I was in Wyoming with the Wyoming DOT, both in materials lab, resident engineer, the standard kind of working grade asphalt we used was AC 20. What does AC 20 mean? Well, that's 2,000 Poises plus or minus 400. So essentially 1,600 to 2,400 had to be the viscosity measurement. And that's a fairly hard asphalt, fairly stiff. We're a lot of truck traffic in Wyoming, and the problem with having a stiff asphalt is in a thermoplastic material, it's great for stability when it's hot out, but what happens when it gets cold and extremely cold? That stiff material doesn't want to give, and the material's trying to contract. So on that minus 25, minus 30 degree morning at sunrise, guess what? You get cracking. So we'd go back and forth. It was kind of funny when you look back is We go AC20. Rutting's a problem. Spec AC20. Spec AC20. Want to resist rutting. Then you kept putting all these roads down with AC20. What happened now? Now you started getting thermal cracking, cold temperature cracking. And now the maintenance foremen were yelling, quit building cracked roads. So AC, go to an AC10, softer. Again, 1,000 poises plus or minus 200 poises. Well, you do that for a while, yeah, the cracking would go down, but guess what? Now you get rutting in high traffic areas, particularly the way we were controlling mixes, and there was no field testing, and it was all Marshall mix design. And so you can kind of see that, and as you walk down a little bit, you can see the viscosity at 275 degrees, which is more of a mixing temperature, transport temperature. And you can see that pen grade right below it. And as you would suspect for the lower viscosity grades, the penetration numbers work the opposite as well. Lower viscosity, softer material, penetration's 220. Higher viscosity material, AC40, the penetration minimum was 40. So just then tests on residue and so forth. So those are kind of your takeaways from that. And it's kind of good to know that, particularly as we use more and more wrap from older and older roads, of what type of residual asphalt is in that wrap. What was it built with? Well, as I mentioned in the Dakotas, if you get east River in South Dakota, eastern North Dakota, a lot of the roads, my grandpa used to call them blacktops, right? County roads. And most of the state highways, if they've been there, and the average age of asphalt roads in the Dakotas is almost 40 years. I mean, they get milled, they get overlaid and so forth, but that original pavement is not touched. And when the average age is 40 years, that means there's a lot of them that are older than that. But if you get down far enough, particularly in the eastern parts of the state, you're probably going to find a road mix that was placed initially. Road mix meaning that asphalt was essentially, gravel was placed in windroad, asphalt was sprayed out, and then it was bladed back and forth and mixed, and then laid with a blade and rolled. And I call it road mix. Some people call it cold mix, but basically the same thing. Well, how do you do that when you have a thermoplastic material? You got to lower the viscosity. You got to get it to flow at ambient temperature, at room type temperatures. And how do you do that? You use cutback asphalts. And all a cutback asphalt is that asphalt residual plus a solvent, some type of basically petroleum solvent. So you can think about it when you get to specifications as cutback's cure. And what you're interested in is getting that residual asphalt in place. The solvent is just a way to deliver it. What happens to the solvent? It evaporates, leaving the residual asphalt in place. So you can think about it as cutback's cure. So you'll see three basic specifications for cutbacks: RC, MC, and SC. So when you see a nomenclature, a prefix like that, you automatically know it's a cutback because of the C. Cutback's cure. It's kind of the cheat there, the hack. So if we look at knowing that those are a combination of residual asphalt and solvent, in an RC, which is termed a rapid cure, the solvent is gasoline or naphtha. So it's that light end product. And MC, which we still use and see in our world, is the solvent is diesel or kerosene. So what do we typically use MC for? Prime, right? You know, when you're building a new road and you have an aggregate base down and it's going to sit there for a while and you want to maintain profile and grade and keep it integral, you're going to shoot a prime. And so we use MC, a medium cure cutback, to shoot the prime. So we cover it up with a little bit of residual asphalt before we can pave it. And the classic smell, I mean, you can drive through it and get close, you know that the prime's been shot because you can smell it. You can smell the diesel or kerosene evaporating off. The RCs, the rapid cures, you see very rarely. You know, gasoline's an expensive product, retails at a much higher value. It's dangerous to shoot because of the low flash point, but it used to be used a lot for chip seals, and it made a great chip seal because the gasoline actually softens that asphalt surface that you're going to chip seal and penetrates. but expensive, dangerous, environmentally insensitive. And then the last one is SC, slow cure, and the solvent in that is a bunker fuel or a fuel oil. And that was used primarily for winter mixes. If I needed to put some mix up in a pile that I had to have over the winter, because if I have a water line break and I gotta dig everything out, but I gotta repave it, and I can't use gravel because it's frozen, and I want something hard surface, so I'm not out there every morning after freezing, is I'd have a pile of SC mix, and I could go in, and after I kind of got through the surface, the skin, I had mix underneath. What happens, though, it takes a long time to cure, right? That's why it would sit in the stockpile. Guess what? It takes a long time to cure on the road, too, so you don't see a lot of that anymore. Then on the suffix, you'll see numbers. Let's just take MC because we still use that, 30, 70, 250, on up to 3,000. That number is actually viscosity. So an MC30 is a relatively liquid product, soft product. Get up to a 3,000, it's a heavier product. So MC70s, 250s, you'd see a lot for prime, for example. Still see the heavier products around for other things like road mix or recycle and place type. So I'm just going to throw up here, this is the AASHTO specification for RC or RC cutback liquid asphalts. Two things to look at, or three things I wanted to point out here is, and they're boxed in, hopefully you can see that on your screen. Second line down is the flash point. If you look at an RC 250, and as I mentioned, the cutter for an RC is gasoline, naphtha. Naphtha is just raw gasoline. What's the flash point? 80 degrees Fahrenheit. So in other words, if that product's out there and it's evaporating, it's exposed to ignition source, boom. So, you know, there were a lot of times, and early on, I didn't see it in person, but I've heard stories from valid sources that the poor distributor person would get up in the morning early, go out, start heating up the tank to shoot RC. Next thing, if they're standing next to the truck, the damn thing explodes. Why? Certain humidity conditions and vaporization. Once it's in the tank, it's going to start breaking. You know, the solvent, in this case the gasoline naphtha, is going to start evaporating off, come out of the tank and circulate in and under the tank. Guess where you light the flames at? Under the tank on the distributor truck, and boom. So that's the safety part of the issue with RCs. But the next box, about midway down, is volume residue from distillation in percent volume by difference. So as you look across there, you'll see is RC70, 55 plus, so a 55 minimum. RC3000, 80% minimum. Think of that, it says residue. That's the amount of asphalt that's in a gallon of that product. So in a gallon of RC70, 55% of it is actually liquid asphalt. The other 45% is gasoline. So, and that's why the viscosity is much more liquid or low. But as you get up to the heavier product, the RC3000, it's 80% asphalt and 20% gasoline that's got to be evaporated off. So key kind of takeaway there is that, you know, the viscosity has its advantages, but you got to shoot more of an RC70 to get the same amount of asphalt in it if you compare it to an RC3000. The other thing, last point down below there, was penetration. You can see the residual asphalt itself was all 80 to 120 pen graded asphalt. So that's a kind of a mid-type softness asphalt. And I bring that out here because we're going to talk about emulsions as well. If we go to MCs, you can kind of see this by the same line. Obviously, our cutback, our solvent now, is a diesel or kerosene or a combination of the two. So our flash point, again, lower viscosity on the left side, higher viscosity on the right side. Lower viscosity means flows easy. Higher viscosity means flows harder or more difficult to flow. On an MC70, for example, the flash point's 100 plus, minimum 100 degrees Fahrenheit. So it still can be dangerous, right? It's the old diesel pump versus a gasoline pump at your local gas station. Middle of summer, somebody spills gasoline on the tarmac, evaporates off almost immediately. Diesel spill on the tarmac, guess what? You're stepping in it 3 days later, right? And get into your car and go, why do I smell diesel? And anyway, that's the difference. You get up to the heavier viscosity products, again, less diesel, more asphalt, higher flash point. Then they run a distillation. You can see that, but the line down at the midpoint, again, one point to always look at is residue from distillation percent volume. So an MC30 only has roughly a minimum of 50% residual asphalt. The other 50% is diesel. If you're shooting an MC250, you want enough solvent to draw that asphalt down in to protect your aggregate base, but you also have to understand the time component. It doesn't become residual asphalt until that diesel evaporates. And it's essentially 2/3 residual asphalt, 1/3 diesel for an MC250. So, and again, next line down is penetration of that residual asphalt. You can see in an MC, the pen graded rating on that residual asphalt is all 120 to 250 pen asphalt. Okay, just one last thing on cutbacks. Again, so you kind of have your basic primer on cutbacks here, is the suffix numbers are the viscosity of the mixed product. And generally, the higher the number, the higher the residual asphalt. And obviously, the stiffer the liquid. But you can also have a suffix that's a alpha character. And that is the modifier that's mixed in with that residual asphalt or that product. R for rubberized, L for latex, P for polymer, so forth. So you could have, for example, a lot of times if they're MCs, the higher MCs, 250, 3000 are used in like process in place, recycle in place type materials. You know, you might see a MC 250P, meaning that the residual asphalt's polymer modified. Okay, well, we already mentioned with solvents, the problem is you're spending a lot of money for that solvent. So the cost is typically higher just to deliver the residual asphalt to wherever you need it. Safety, especially when you start looking at RCs and MCs, the flash point can create its own safety issue. Then the third is environmental. Obviously, you know, we've gone to a lot more. I mean, on the gas tank on your vehicle, there's a condensation collection system. So your gasoline vapor doesn't escape the car and go into the atmosphere. You get into the front range of Colorado, the valleys of California, the East Coast, you know, they're under strict emission standards, particulate matter and emission standards, and they do not, by law, allow the use of cutbacks in a lot of areas. So the transformation occurred to what are called emulsion or emulsified asphalts. And that's just a combination of asphalt, the residual asphalt, in water, and then some type of emulsification agent. Why the emulsifier is oil and water don't mix, right? So, I mean, you've probably been hearing that as a saying for a long time. Well, oil and water don't mix, and they don't. But if you put enough shear force in and some type of emulsification agent, and you kind of think of that as a basic soap product, is you can get the asphalt to suspend in the water. It doesn't mix with the water, it suspends in the water. And that's the basic mechanics behind an emulsion. So kind of the cheat here, the hack, is think of emulsions as setting or breaking. They don't become residual asphalt, which is what you want, until the water breaks off or that emulsion sets. So from a specification standpoint, plan sheet, materials and rates, you'll see an S. And if you see the S, you automatically know from an asphalt product that's an emulsion, because emulsion's set. And the prefix alpha is how fast. Rapid set, medium set, slow set. And there's times and uses and functions for all three of those. Then the ladder numeric is a viscosity range. And with emulsions, it's pretty simple. basically two ranges. We'll get into the specification here in a second. And we'll talk about that 1H here in a second as well. The other thing is emulsions and the emulsification agents are, if you just see a 2-digit alpha on the prefix, the electrical charge is anionic, negative. If you see the third letter, the C in front of it, it means obviously cationic or plus. So if you think about the battery on your car, you got a plus, positive terminal, negative terminal. So, and that's just the small electrical charge that's basically in that product. And there's a time and a use for both of these. One thing to remember is in a lot of cases we're using emulsified asphalt on an aggregate. And aggregates in general have a small negative charge. So if you're shooting the asphalt on that aggregate, generally you kind of want a small cationic charge, right? Opposites attract. So something to remember there. So again, if the letter C is in there, it's a cationic, has a small positive charge. So if we look at the specification, looking at the top, this is an anionic, so negative charge emulsified asphalt. You can see those ranges, RS, MS, and SS. So rapid setting, medium setting, slow setting. See two ranges on RS, RS1, RS2, one grade on medium set, MS2, and then SS, 2 grades, and we'll get to that here in a second. But the important line here, and the important thing to remember, and what do we use emulsions for a lot, is for chip sealing and for tack coat. Tack coat is the oil we put down to bind 2 layers, chemically weld 2 layers of asphalt, 2 lifts of asphalt together. So important thing in here is distillation residue. Well, what does that mean? Percent by weight here. By weight, not by volume, as we looked at in cutbacks, by weight. Well, the residue is the asphalt. So in that gallon of emulsion, we weigh that out, at least 57% of it has to be residual asphalt for an RS1. And then on up the line. So a lot of times what we use is, okay, we need to shoot it heavier if we want so much asphalt on the road, and it's only 60% asphalt and 40% water. Guess what? We need to increase that shot rate to get that target of residual asphalt on the road. Important thing to remember for tack coat. Okay, we'll get into that a little bit later, and we get into it in the inspection class in detail. So again, remember, because a lot of times with tack coat, what do we use for tack coat? That bond between 2 layers. We shoot an SS, a slow set, right? First step in paving, overlay job. You got to clean the road. Next step is got to shoot the tack. Next step is we got to wait till the tack breaks. Now we can start paving. Well, understand that sometimes they shoot that tack. You're shooting a relatively small amount of asphalt on the road for a tack. To get it through the spray bar in the distributor truck, they'll dilute it. They'll put more water in, and that'll work. You don't want to leave it in the tank very long when you do that, but you dilute it to put more water in. Now I can spray it out at a higher rate. I keep the pump and the spray bars working at a much higher volume, so I get more uniform shot rate, or spread rate, I should say. Well, remember, you're only starting with 57% asphalt. So my shot rate, and what you'll see on plan sheets typically is a recommendation for tack rate, and that's a minimum. And it'll say 0.06 gallons per square yard, for example. Well, that's six hundredths of a gallon per square yard of pavement. That's based on this undiluted shot rate. In other words, it's already worked in that it's 57% asphalt, basically. If I dilute it further than that before I shoot it, I got to increase my shot rate. Last thing on this slide is, at the bottom boxed in there, is the penetration. That's the residue test. What's the residue? The asphalt cement. So you can see in the first 4 columns, the residue, the asphalt, is a pen graded asphalt at 100 to 200 penetration. So it's 100 to 200 pen asphalt, except for that last one, SS1H. The residual in that SS1H is a 40 to 90 pen asphalt, much stiffer, right? So the takeaway here is that if I'm tacking and I'm on a city street, or I'm tacking across an intersection on a rural job, or I got a lot of cross traffic, and every time a construction job starts in rural area, it doesn't matter if you're in the middle of nowhere, all of a sudden the trucks start hauling grain out of that field approach. Everybody's got to come out of that field approach, and now you're tracking. Well, to not eliminate, but limit the tracking, use an SS1H. It's a harder pen residual asphalt, less likely to track. So that's why you see on most recommendations and specifications, plan notes, is they allow the use of a CSS or a SS1 or 1H. So it gives you that option to shoot a 1H, which is going to be a stiffer pen graded asphalt, which will accommodate less tracking. So important point to remember. Okay, and I'll finish that off. Here's the other side of the coin, positive charge or cationic charge, CSS. And again, we kind of covered the first couple columns here. The CMS, the 2 grades of CMS here for medium set are primarily because of on-the-road products like process in place or cold in place recycling. But the far right is the slow set, SS1, SS1H, in this case CSS, cationic CSS1H. So kind of same basic premise here. The 1H has a 40 to 90 penetration residual asphalt. What does the CSS give you? A slight positive charge. So if you're on a project and you're having problems with tack, breaking, and breaking uniformly, in other words, the water coming out, a lot of times just switch to a CSS. Since most aggregate is light negative charge and you're shooting a positive charge, CSS1H, guess what? Your problem goes away because opposites attract and you'll get a more uniform break. So, Shay or Sharon, any questions at this point coming through?
Does asphalt paving have advantages, disadvantages compared to Portland concrete paving?
I say advantages because it's so, I mean, it's kind of interesting in the pavement design world, they don't call it asphalt, they don't call it concrete. They call it flexible pavement versus, I'm not even going to say the other one. So, you know, the thing about asphalt is it's so flexible. I mean, from a pavement preservation standpoint, from a pavement rehabilitation standpoint, and basically all the numbers show it is that you know, it's much cheaper, much more economical to place asphalt pavements. I mean, 97% of the pavements across the United States are asphalt. And I understand I've built concrete pavements. By the way, rigid is what they're called in the pavement design world. And I built them, I designed concrete mixes, tested them. It's a matter of cost and constructability, and more constructability is the big issue, is time to construct. Is, you know, asphalt roads, they can be maintained and built under traffic. I mean, we do it all the time, right? 2-lane roads, head-to-head traffic during the day with a pilot car. You know, very rarely do we close roads. The other thing is very rarely are asphalt roads reconstructed. As I mentioned, the average age is approaching 40 years. So, I mean, yeah, they're added to, they're overlaid, they're milled and filled, but they're still there. The other thing is the value of asphalt is retained forever. Most of it's almost like a certificate of deposit that we have in both states. Is those roads were built with asphalt liquid that basically cost probably $10 a ton. And the aggregate's already there, obviously, for the road. So all of that can be reclaimed and rebuilt into a pavement. It doesn't have to be removed, recrushed, put into cushion course or landfilled or anything else. Basically I mentioned process in place or cold in place recycling. You can actually pick it up and lay it right back down and capture all the value that you put into that pavement. And the value that's in that pavement obviously is for its rideability, but for something that you bought 30, 40 years ago for $5 a ton versus $400 a ton, for example, for the asphalt liquid. And if you look at mixed ton, a ton of asphalt mix, everything included, all three A's, the asphalt, the aggregate, and the air, the mixing process, mix design, placement, haul, paving, compaction, is roughly somewhere, depending on the mix type and location, say 55 to 75 bucks a ton for in place. If you put 20% wrap in, you drop that probably by 10 or 15%. Now you're talking 45 bucks to 65, 67 bucks a ton in place. And in the Dakotas, we pay for the asphalt as a separate bid item. Most states, it's just composite, the oil subsidiary. If you look at that mixed ton, again, and it changes depending on the market, but roughly half the value of that mix, or half the cost, is the asphalt side, the first A. So in a $75 per ton total cost in place asphalt ton, 50% of it is the liquid asphalt. And that goes up and down depending on the market. But the interesting thing is a lot of our roads, refineries, and I say this from working at Texaco too, is refineries, the asphalt's a waste product. In the old days, you know what we got charged for asphalt? Was how much it cost to haul it from the refinery to wherever you were using it. It was essentially a haul cost. The refineries just didn't want it in their tanks, particularly in the northern climates, because a refinery runs 724, 365. So in the winter, obviously there's not a lot of demand for asphalt, so what do you have to do? You tank it. Just to close that off is now everything we're bringing up to recycle, we spent $5 or less on, and it's worth $400 a ton, just the liquid side of the equation now. So anyway, next question then.
What is the price difference between SS1 versus SS1H?
Actually, very little difference. I mean, market can dictate it, but in a lot of cases, the SS1H is cheaper to produce because it's a harder asphalt. It's normally the harder the asphalt, the more difficult it is to market. So, but it's market driven, but generally there's no difference.
How long will it take the different cutbacks and emulsions to be able to pave over in relation to each other? Maybe the set time or cure time.
Yeah, cutbacks, again, if you look in the spec book, standard specifications, when you're shooting MC for a prime, most states dictate a curing period, 72 or 96 hours, 3 or 4 days. And that's because you're trying to evaporate diesel fuel. Well, the more diesel fuel you have in it, right, the lower the grade of the MC, longer it's going to take. But temperature, humidity, time of year, all impact that. But in general, 3 to 4 days is probably a pretty good rough rule of thumb on MCs. RCs, it was, literally minutes, seconds. That's why it was used for chip seals. With emulsions chemically break. That's what the emulsification agent does. You want it to be stable when it's shipping to your site. You want to be stable in your storage tank on your site, but when you spray it out of the distributor, then you want it to break. You want the water to come out. And that's typically, I think I've got some pictures here in a second, but typically it's kind of the brown to black stage. When you shoot it out, the tack out, it kind of looks a little brownish. That's just the reflectivity. When the water comes out, it's black. It's residual asphalt on the road. You'll see that in this picture. And that, mid-season, when it's hot out and you got 14 hours of sunlight, and it's typically dry, humidity's down, that can be literally minutes. But early season, late season, extremely low humidity, low wind, they can be longer. And that's, one of the things is an emulsion break. The only story I can tell on that is when I was in Casper, when I was district maintenance engineer in Casper, we used to do a lot, and this was on I-25, which is north and south, but from Casper it's east-west over to Douglas. But between Douglas and Casper and Glenrock, we were doing what we called half soles. In other words, we were doing paver laid patch just in the driving lane, the outside lane. Well, Wyoming rotates the crown on the interstate from center line to median, not center line of the two lanes. So in other words, it's a constant slope from left side to right side, 2%, 3%, whatever the crown is. So when you do a half sole, kind of one lane overlay, if you want to call it, the outside lane, you build a little dam at center line. And it does rain in Wyoming once in a while. And so if you get a rainstorm, you get this ponding at center line. So what we started doing was chip sealing the passing lane at the same time. So it'd be a more uniform profile. While we were doing that, we'd finished, 2-3 miles of half sole patch, and we're trying to chip seal the driving lane. And all of a sudden it's like 5 o'clock at night, and this is June or July, and we can't get the chips down because it hasn't broke. Well, what we ended up doing, of course, we had brooms out there, motorized brooms, and we had water tanks on them, spray bars. And I said, we got to open this road up. We don't have overnight traffic control available or on site. So what I told them to do was to take the motorized broom, put the broom core up so it's not hitting the road, but put the spray bars on so you're putting a light spray of water out, misting. And we did that over the top, took three motorized brooms in echelon, did that, and it broke right away. Sounds counterintuitive, but the fact, it's so dry in Wyoming, you put a little bit of more humidity, the sweet spot, and that water just broke out of the emulsion, just like that. Then we laid the chips and rolled it real quick. So the time on the break is the slow set is set up, so you're going to get some time. Once you shoot it, the water. The rapid set, the RSs, what do we chip seal with? Typically in the Dakotas is CRS, cationic rapid set, CRS2 or CRS2P, meaning polymer modified. So again, rapid set can be almost instantaneous. Once it hits atmosphere and hits the road, the water's breaking out. So hope that answered the question. There is a fourth category called high float emulsions. High float is actually a test, and they're still around. South Dakota uses some, the nomenclature is HF, MS, typically high float medium set. South Dakota has a different nomenclature for it. They use it primarily in south central South Dakota because of the aggregates that are available for chip seals. And that's how high floats developed. Emulsions were the greatest thing since sliced bread because they were much cheaper, right? You're not paying for gasoline to evaporate. Water's a lot cheaper, a lot safer, a lot more environmentally friendly. I know the first chip seals we did in Wyoming with emulsions, though, we had a big problem because our chips were too dirty. So all of a sudden, snowplows are peeling that thing off like, peanut butter off a slice of bread. And we came to find out, we got to use a different emulsion. And high floats were kind of designed to be a little more dust tolerant, but more and more states have moved to better specifications, better designs for chip seals. The amount of high floats have gone away, but there's still a use for them out there. And then, as you see there, high float medium set, high float rapid set. You can also see an alpha suffix, and again, that's the modification of the residual asphalt. Rubberized polymer latex modified. So as I mentioned, for chip seals across the Dakotas, a lot of times you'll see a CRS, cationic rapid set, 2, viscosity range 2, P, polymer modified, CRS2P. There's just a picture of a tack coat. And this is outside of Mott, North Dakota, kind of south central, southwest North Dakota. And, really good shot rate, real good even distribution. And this was first shot, and I tried to look for my pictures of the distributor going as well. But, turns from brown to black. The cure test is for a tack coat, it's got to weld the 2 layers. So you need the residual asphalt on the road. And that's why I wear my old boots when I'm out on jobs like this, is because I step in it. If I don't get some crawling asphalt up the soles of those boots, there ain't enough tack there. Okay, kind of finishing off this on the asphalt side and then leaving a little time for questions, is we need to get into the paving grade asphalts. So we talked about penetration grade, shortened to pen here, viscosity graded, VIS here. So if you remember, our penetration test is run at 77 degrees Fahrenheit, which is 25 degrees centigrade. So if we had spec'd a pen graded asphalt meeting a certain range, 85 to 100 say, both A and C in this diagram would meet the requirement of our specification, right? But same traffic, same roadway, what happens to those 2 asphalts as they get those extremely cold winter temperatures? C is going to crack quicker, right? Because its cold temperature properties are much more brittle. A is much softer, even though they grade and spec the same for pen grade. So you can build the same road, same spec, same thickness, everything the same, and everything meets specification. But I'm sure hoping that I got an A asphalt and not a C asphalt from this chart when I get to cold temperature cracking. Conversely though, is when it gets extremely hot in the summer, right? We run the viscosity at 60 degrees and kinematic at 135 degrees centigrade. So that's 270 and 140 basically. Is if I just use viscosity to grade it and specify it, I've got B and C, right? They meet the same viscosity specification requirement. And just as we talked about with pen graded, the problem here is that B is much more soft, C is much more brittle, and therefore susceptible to cold temperature thermal cracking. But when it gets to the rutting side, the high temperature side, the middle of the summer, is C is much softer as well. So it's more susceptible to rutting. And so this 1 point specification just wasn't going to work, especially in our world. In the northern upper Great Plains and the northern Rocky Mountains, is you're kind of damned if you do, damned if you don't. You work one side of the equation to resist rutting, guess what? Now my thermal cracking's going wild. Try and avoid thermal cracking, now my rutting's going wild. So with a combination of PG binder, super pave, and better control of the mix, better design of the mix, we can get both. And that was the kind of the initiative of PG binders, performance graded binders. Depending on which spec we used, it was a single point measure. Unfortunately, in both of those, none of them measured a low temperature property, which can be the biggest killer of pavements in the Dakotas, right? It's just that one extremely low temperature, and that one season, that's a bad winter. And then we got into more modified asphalts. And the viscosity system, pen system, don't handle or characterize modified asphalts. The other thing is more and more of these products, and I was in the lab in Cheyenne at the time, it seemed like every week there were 3 new snake oil salesmen. Put this in, carbon black, sulfur extended, everything you can think of, including polymer, some of them that we use now. So states started writing different specs because they had tested and tried different modifiers. And now you had suppliers trying to figure out which state they were sending stuff to and which specs they were trying to meet. The other thing is because asphalt's a thermoplastic material, viscoelastic material, it changes properties with age. And neither of those previous specs took into account long-term aging. Generally, over time, asphalt oxidizes, it becomes stiffer. That's why if the pavement quote is a rudder, is if you make it through the first couple summers, guess what? You're fine because it's going to stiffen as it ages. So again, the basic asphalt binder specification kind of laid out here. It's a grading system based on climate and traffic loading. So the PG designates that, hey, it meets the performance graded binder spec. And this one, South Dakota, they use what's commonly termed PG plus, AASHTO spec, and I'll get to that in a second. But the first number there is actually the average 7-day maximum pavement design temperature. So based on where you're at in its climate and the traffic loading, that's a temperature in degrees Celsius. So I know, okay, I need 58 degrees Celsius to keep my stability, resist rutting. The second number, that's not a hyphen, that's a negative number. It's a negative 28 degrees C. That's the minimum air or pavement design temp. And when I say air or pavement, is the most susceptible part of the pavement to thermal cracking is right at the interface between the top of the pavement and the air. It's that cold, cold, cold January morning right before sunrise or right after sunrise. And the cracking starts from the top and works down because that's the maximum stress of that pavement trying to contract. So that's the basic system, 58, average 7-day. Maximum pavement, 28, minus 28, low pavement. North Dakota has a little bit of twist on this, as do some other states. They use what's called AASHTO M332, which is also called, and I'll show that here in a second, the Massacre MSCR system. Same kind of basic layout, PG for performance grade. First number is an average 7-day maximum pavement temperature. Second number is a negative pavement temperature, and these again are degrees centigrade or Celsius. But they add this suffix after the high temp number, and it'll be an S, H, V, or E. And that designates whether it's the loading condition. S is standard, H is high, V is very high, E is extremely high, and I'll get to that here in a second. So what are we looking at? We can go in and I'll show you the output page here in a second. For any pavement, any location, we can calculate through the algorithm what this highest 7-day average is, and we can do it on a probability basis. You know, you see a standard bell curve on the low temperature side, on the high temperature side. How reliable do we want it to be? You know, nature changes, variable, we get variability. You know, if we want to be extremely conservative, we use the very outer edges. If we want to be relatively standard, guess what? We use the middle of those two normal curves or bell curves. And that's just kind of the layout of what this algorithm does. And again, these are pavement temperatures. Going off of actually the algorithm, and I'll show you the software that does that here. Will, depending on where we're at, and time of year and so forth, we'll run that number for us so that we get both low pavement temperature, high 7-day average pavement temperature. And then I talked about that, either the very extreme outsides gives us the most reliability. This is an AASHTO concept for pavement design as well, and maintenance. It is this reliability concept. And so if we're on a high volume road with a lot of traffic, we want very high reliability. So that'll tell us which grades we go to as well. The other thing we kind of have to bring into play here with asphalt is, because it is a viscoelastic material, is the flow behavior and the rate of flow. You know, a constant force, I call it the Harley kickstand of impact. Middle of the summer, somebody's got this $25,000, $30,000 Harley, and they go in to eat lunch and they're put the kickstand on. You got all that load on a real small footprint. And if it stays like that for an hour, all of a sudden somebody comes out and sees their $30,000 Harley laying on its side, and they start looking for people. And that's this kind of rate of loading behavior. And that's why you see a lot of problems, usually of stability, will first occur in an area of starting and stopping, whether that's a stop sign or a signal light. And so the original PG binder protocol was that if I had extremely high truck traffic, out of my total ADT, average daily traffic, a large percentage was truck traffic, I would do what's called a grade bump. I'd take that 58C, for example, and bump it up to a 64. And the PG grades work in 6-degree increments. So you go 58, 64, 70 on the high temperature side, minus 22, minus 28, minus 34, basically, for our part of the world on the low temperature side. And then if you had an area that was extremely high loading, like a start and stop, is you would bump it again. So now your 58 became a 70. And that was the way you compensated to account for those pavement characteristics and pavement loadings. Well, we don't get pavements that reach 70 degrees centigrade in our part of the world. And so essentially we're trying to fool the system. And so what happened, or what came out of that, was kind of this MSCR method, multiple stress creep recovery. But I'll get into that here in a second. But basically what PG Binder did as a specification, as a testing method, is tried to accommodate the asphalt liquid under all conditions. Far left there is the extremely cold pavement temperature, where that pavement's trying to contract, maximizing those stresses in that pavement, which at some point doesn't take traffic, pavement will snap. And, you know, might be on 50 foot, it's a transverse crack on a roadway, and might be 50 foot to 200 foot spacings. And then next step to the left was a test that looks at, okay, what about normal operating pavement conditions? We want to assure that. And then third and fourth to the right, the third one is what happens at extremely high pavement temperature in the summer. Or far to the right, the fourth one to the right, is what about when we're pumping and storing that and we're running it through a drum with the burner blowing hot superheated dry aggregate through it. So it accommodated all of those conditions. This is just the layout. You don't have to memorize this. It's kind of the range of testing based on PG grade. You got still got the flash point, but you're using rotational viscosity, and then DSR was the big one, dynamic shear rheometer. It's a G star sine theta test, but we do that both for the initial asphalt, the original asphalt, but also artificially age it and test it and run it again, and it has to meet those specifications. So we account for that aging property as well. So I mentioned modified binders. How do we get there? Well, rule of thumb, if you add those two numbers together, the absolute value of those two numbers, and they're getting around 90, and particularly if they're very far above 90, neat asphalt has to be modified, some type of modifier to get that type of temperature range. So when you start seeing a pretty big range between that high temperature and low temperature number, you probably have a modified asphalt. So how do we pick it? Well, based on climate, roadway, traffic loading, we use what's called, and write this down, would you, everybody, is LTPP bind. And if you Google that, you can get to software through the Federal Highway Administration webpage, Turner Fairbanks, and it's a free shareware. You'll see it here in a second. But North Dakota uses what's called the PG Massacre specification, to use the slang, multiple stress creep recovery test. South Dakota uses what's called PG Plus, which is essentially the PG specification as well as specification controls on the modification or modifier utilized in the neat asphalt. If you bring up, and you can download this program, LTPP bind, this is what it looks like. You can see that literally thousands of weather stations across the United States and Canada. And you just put your target on wherever you're at. And in this case, I picked a spot right at the border. It's near Eureka, South Dakota, McPherson County, just east of the Missouri River. And it'll give you the 5 closest weather stations. And you can see them listed there. And for those 5 stations, it gives you the average and the deviation of the high temperature and low temperature. Also the temperature drop, how fast the temperature drops. And for those of you that are still using concrete, of course, strictly in structural concrete for bridges and stuff, it gives you degree days too. But at the bottom third of that is what we're looking for. Is it gives us, for that particular area, this case Eureka, South Dakota, is okay for its temperature and climatic conditions. It should, the algorithm will rate me out at 52.7 to minus 25.4, which means for 50% reliability, I should be using a 58 minus 28 oil. And if I want to bump it up, essentially it's the low temperature side, which makes sense, right? Eureka is 58 minus 34. The numbers in parentheses are the actual reliability of that particular temperature for that particular area. So for the 50% reliability, the 58 minus 28, the low temperature number is only 79% reliable. So that's why you see the bump to the minus 34 in cold temperatures. So that's the one output you get from it. You can also get specific. We talked about rate of loading. The other thing, cold temperature effects drop with depth into the pavement, right? If I'm doing 2 or 3 2-inch lifts, I don't need the minus 34 in the bottom 2 lifts, because the lower I go in that pavement structure, the closer I get to what temperature? 0 degrees centigrade, right? Frost line, 32 degrees Fahrenheit. So I can go in and based upon what reliability, high traffic, high volume road versus a low traffic road, and depth in, and the rate of loading, fast versus slow, I can compensate this and come up with a fairly accurate PG binder grade selection. In this particular instance, it was 58 minus 28. You can do this for any place. This is really good if you're a consultant on the DOT design or making recommendations. You know, I urge you to take a look at this program. It's free download, LTPP bind. It's got a lot of other good information as well. You can map out the PG grade categories across the state. So just wanted to bring that up. Last thing was, both states are members of what's called the Combined States Binder Group. It's a group of states, including, as you see listed there. What it does is it combines from the asphalt production side, the QA element is the producer or refiner, and these states have agreed upon a common quality assurance and testing procedure, and they do round robin testing between the state highway agencies. And the idea behind this is so that we kind of marriage cost and flexibility. In other words, if you order a 58 minus 28 in Minnesota, it's the same as South Dakota, it's the same as North Dakota type thing, which saves money. So this is just the basic background on it. I would urge counties and cities to evaluate this. I mean, when this first came out, I was working up and down the eastern corridor, the Big Sioux River and the Red River and the Dakotas, saying, hey, if you look at those numbers for city streets or counties, a minus 34, if you want reliability to keep away from cold temperature cracking, you should be building with minus 34 on your cold temperature end, because those areas tend to be the coldest part of the state. You get up to the northern border and North Dakota Canadian border, it's the same way, and you can look at it on that map. But the one thing for states, counties, consultants is when you spec a job, you can refer to the DOT standard specifications. Well, that's good. With it, it's going to carry the specification requirement. In South Dakota, that's PG plus, and North Dakota, that's PG Massacre or AASHTO 332. But you also have to spec a grade. You can't just refer to the standard specification book on your project without putting a PG binder grade into your plans and specs, because that's not in the spec book, that's in the plans, and that's how the DOT does it. And so if you don't spec it, you're going to get whatever's cheapest on the market, and that's not what you want for your road.